Physicists are famous for building some big honkin' experiments. Take, for example, the Large Hadron Collider. That thing is so big, they had to bury it under 2 separate countries, all to study some of the smallest particles in the universe. But the LHC is nothing compared to an experiment called KM3NET, because that thing spans the length of the entire Mediterranean Sea. And even though it's still under construction, it's already making some record-breaking discoveries. Over the millennia, humanity has figured out a lot about how reality works, but despite physicists having multiple theories that do a really good job of explaining most things, those theories are also incomplete. Which is actually kind of great for physicists, because if not, they'd be out of the job. And how boring would life be if we didn't have any questions left to answer? The theory we're going to focus on today is called the Standard Model of Particle Physics. It tells us about electrons, quarks, and other subatomic particles, what their properties are, and how they interact with one another. It is by far the best model we have for this area of knowledge, but there are several major phenomena that it just can't explain, like dark energy and dark matter, and the nature of nature's least massive, most elusive particles, neutrinos. For example, the Standard Model assumes that neutrinos don't have any mass, but we know from experiments that they do. We don't know how much mass each flavor of neutrino has, but we know that it's not zero. And that gap in knowledge comes from the fact that it's really hard to study neutrinos. They're everywhere, streaming through the whole cosmos, including your body right now, but they absolutely hate interacting with other particles, be they inside a science experiment, or inside of a mountain, or a dog, or a hat. About 100 trillion neutrinos pass through you every second. So scientists would love to just capture a neutrino directly and ask it what its deal is. Bring it into the station, put it in the interrogation room, good cop, bad cop. We're gonna figure out what's going on. I mean, as much as you can ask a subatomic particle anything. And they've realized that the best chance of doing that is to go big. Humongous, gargantuan, titanic. Maybe not titanic, though chunks of ice can be involved. Sorry. The bigger your detector, the more chances a neutrino will interact with an atom inside the detector. So over the same time span, you'll have more data points to analyze. For a sort of baseline, let's look at Super K in Japan. It houses 20 Olympic swimming pools of water to help its detectors capture neutrinos. Basically, a massive vat of liquid greatly increases the chance that a neutrino will collide with a particle within the observation zone. And using water specifically helps us visualize the aftermath of that collision. We're going to get to that in a minute. But even with all that water, Super K might capture 30 neutrinos in a typical day. That sounds pretty pitiful compared to the number of neutrinos moving through a much smaller human body, but that's how ghostly these particles are. So to get even bigger, some organizations have swapped fluid-filled detectors for burying their detectors in pre-existing bodies of water, like Lake Baikal, home to the Baikal Deep Underwater Neutrino Telescope. IceCube near the South Pole, which is a block of solid water. And then there's Antares in the Mediterranean off the coast of France. It was a 14-year pilot project decommissioned in 2022 to make way for something even bigger. That's right, the KM3NET, which, by the way, gets its name from its sheer size. Its thousands of individual sensors will be spread over many cubic kilometers of seawater. KM3 stands for kilometer cubed, and the NET is neutrino telescope. Each of these sensors is a 0.44 meter wide glass orb full of delicate photon detecting equipment. Chains of them are arranged in a 3D pattern and anchored along the bottom of the sea at depths between 2.5 and 3.5 kilometers. The largest cluster is off the coast of Sicily and spans a full cubic kilometer of seawater. That's equivalent to 400,000 Olympic pools. Meanwhile, the cluster off the shore of Toulon, France is smaller, only 2,800 Olympic pools, but inside that volume it has a denser array of detectors which allows for more detailed measurements. And finally, there are several test detectors located off the coast of Peloponnese, Greece. The research collaborations plan to install a full cluster there in the coming years, assuming they can get the funding. So yes, this thing will indeed span most of the Mediterranean Sea. As for deploying the detectors into the sea, let's just say that has been challenging. They have to navigate the detectors to the exact right position, secure them to the seabed, and ensure they don't get tangled up. The team even had to design a special launch vehicle just for this job. And that job begins with the construction of a string of 18 orbs wound up around a big spherical frame. Then an anchor sinks the whole apparatus to the seabed so the frame can slowly unwind to deploy each orb on the string. Each string is connected to others via cables, and the entire cluster is linked to the shore via a 100-kilometer cable that transmits data and provides power. Once the orbs are online, they can start their passive search for flashes of a special blue light called Cherenkov radiation. See, light travels at different speeds, depending on what it's traveling through. It's fastest when it's traveling through the vacuum of outer space, and it has to slow down when it stumbles upon a different medium, like a big body of water. The exact speed depends on the medium's properties, as well as the wavelength of the light doing the traveling. In water, it's about 25% slower than in a vacuum. But subatomic particles, like our precious neutrinos, don't have to abide by this new speed limit. And when a charged particle passes through a medium like water, if it's traveling faster than light can travel in water, something weird happens. It generates a cone of eerie bluish light. Basically, the particle jostles the atoms in the medium, giving those atoms some of its energy, and that energy then gets released as a wavefront of visible light. As a particle races through the medium, it creates a track of Cherenkov light. And over the years, scientists have gotten really good at looking at those tracks and reconstructing the event that made them. Thanks to KM3net's 3D configuration, all those strings of orbs floating in a grid, physicists can trace a particle's exact trajectory. And by combining the trajectory's shape and the amount of energy released as light, they can reverse engineer the type of particle. But wait a minute. I hear you scream through the internet. You said Cherenkov radiation is created when charged particles travel faster than light, but you also said neutrinos are neutral. That's why they call them neutrinos. Yes, I did say that. The KM3net's detectors can't directly spot neutrinos, but in certain situations, neutrinos can react with other kinds of particles to create new charged particles, like the famous electron, or its nowhere near as famous larger sibling, the muon. And those particles can not only produce Cherenkov radiation, they produce tracks that are easily distinguishable from both one another and any other kinds of random blue light. Like, for example, light made by the bioluminescent Mediterranean organisms that might wander through the detector. Didn't you worry about that? Did you think about that? Turns out they did too. They're smart, these scientists. And this giant experiment has already discovered some things, and I'm going to tell you about that right after we do a real quick ad. This SciShow video is supported by Brilliant, an online learning platform that helps you build real knowledge through lessons you will actually remember. Brilliant's courses are designed to help you stay engaged and excited to learn, using strategies and methods designed to help you build skills fast. They've got classes developed by professionals from places like MIT, Caltech, Microsoft, Google, and more, so they know what they're talking about. If you want to learn from the pros, it's easy with Brilliant's interactive lessons on everything from math and science to data analysis and programming. And there's always more classes being added. To try Brilliant for free, visit brilliant.org/scishow, scan the QR code on screen, or click the link in the video description. You'll also get 20% off an annual premium subscription. Even though the KM3net hasn't yet reached its final form, it's been collecting data since 2017, and on February 13th, 2023, it witnessed a truly extraordinary event, which the scientists filed under the catalog name KM3230213A. I don't love that, so we're going to call it the event from here on out. The event manifested as a nearly horizontal streak of Cherenkov radiation cutting across the Italian cluster and lighting up more than a third of its detectors. The research team concluded that the light had been created by a muon, specifically a muon created by a neutrino, the most energetic neutrino ever detected. But again, they only had the one muon data to go off of, but the team estimates that the neutrino's energy had been around 220 peta-electron volts. That unit doesn't mean a whole lot lot to people who aren't particle physicists, but from what I've heard, it's enormous. Roughly 20 times more energy than the last record holder. After 2 years of data analysis, the discovery was finally published in the journal Nature, which, sure, sounds like an obnoxiously long wait, but if you found an event this shocking, you would want to not just double, but septuple check your work. The team also spent time running the stats for an event this energetic, cross-checked catalogs of other high-energy events, and searched for potential origin sources of the muon's parent neutrino. To determine how much energy the neutrino must have had, they ran a bunch of simulations, but because they didn't exactly know where the neutrino created the muon, the simulations had to cover a ton of different scenarios. This is all work that you want to be very careful about. Plus, with huge collaborations like the KM3 it's super important for everyone on the team to review the results. And imagine coordinating the opinions of 286 paper authors. I think that sounds very stressful, but it was a necessary hurdle to overcome because the event might have been the result of a class of neutrinos that until now only existed in theory. There's a lot that we don't know about how neutrinos are born out in the universe. It's a very active area of astroparticle physics research. But we have some theories that could describe most of the high-energy cosmic neutrinos that we observe experimentally. Physicists think that high-energy neutrinos might be produced in cosmic accelerators, like supermassive black holes, supernova, or neutron stars emitting gamma-ray bursts. The idea is that these powerful objects accelerate protons to incredibly high speeds, creating cosmic rays with massive amounts of energy. Then, when a cosmic ray inevitably bumps into some other particle floating around in space, it can trigger interactions that produce high-energy neutrinos. It's a solid idea, but unfortunately, get this, it cannot explain the event. Because if you run the numbers based on all of our existing theories about neutrino generation, observing a neutrino with that much energy is really, really unlikely. So unlikely that it would take 70 years of continuously running the KM3 net to maybe spot an event like this. But the KM3 net did see this event, and it happened after only 335 days of data collection. This led physicists to propose that the event could be part of a class of neutrinos that's never been detected before. If a cosmic ray were to interact with a photon from the cosmic microwave background, it could produce what's called a cosmogenic neutrino. The cosmic microwave background, or CMB, is made of photons that have been bouncing around ever since the universe was a mere 380,000 years old. In other words, they're around 13.8 billion years old. These CMB photons are literally everywhere and relatively low energy, hence the word background. In fact, right before scientists discovered the thing, the signal was briefly thought to be static caused by bird poop on a satellite dish. Anyway, if an ultra-high energy cosmic ray were to perfectly pinball off of one of these ancient CMB photons floating around, the resulting particles, including cosmogenic neutrinos, would carry an enormous amount of energy. If the event really is our first photo of a cosmogenic neutrino, then the KM3 net has unlocked an entirely new sector of astronomy and cosmology for us to explore. Regardless of the event's exact origins, this is an incredibly exciting detection. The KM3 net is already observing the most energetic neutrinos in the universe, and it is still under construction. And of course, it is not the only neutrino detector out there. It's part of a collaboration called the Global Neutrino Network, an alliance of neutrino detectors all around the world that are coordinating their research efforts. Who knows? Maybe one day, scientists will turn an even bigger body of water into a particle physics experiment. I'm looking at you, Caribbean. We're coming. And then we're gonna have a margarita on the beach.